Picture this. It's 6 p.m. The sun has just set, and out in the fields, millions of solar panels have completely stopped producing power. But right at this exact moment, you get home, your neighbors get home, air conditioners kick into overdrive, TVs flip on, and peak evening demand for electricity just absolutely surges. Welcome to This Explainer. Today, we're looking at the $50 billion solution to this exact massive problem: battery energy storage systems, or BESS for short.
Okay, let's dive right into our roadmap for This Explainer. We're going to start with the duck curve problem, figure out what a BESS actually is, walk through how these massive grid batteries work, examine battery chemistry and grid safety, and finally, take a look at the future of energy storage.
Section 1. The duck curve problem. This is the big existential threat facing modern renewables. So what really happens to our grid when the sun goes down but our demand for power shoots straight up? Well, this exposes the absolute fundamental flaw of solar and wind energy. You see, unlike water sitting in a giant reservoir, electricity on the grid has to be consumed the exact millisecond it's produced. If you don't have a buffer, the whole system is completely at the mercy of the weather and the time of day.
This massive mismatch creates what folks in the industry call the duck curve. The belly of the duck is midday, right? That's when solar floods the grid, pushing the net demand from traditional power plants way, way down. But the neck of the duck, that is the steep, incredibly dangerous ramp-up in the evening when solar drops to zero just as everyone gets home. Because of this, grid operators are forced into curtailment, meaning they literally have to tell solar farms to turn off, throwing away billions of dollars of clean energy just to keep the grid from destabilization. It's crazy.
Moving on to Section 2. What is a BESS? The ultimate answer to our problem.
And this brilliantly illustrates the concept. Think of a BESS kind of like a giant municipal water tank. A water tank stores excess water when a supply is high, right? That way, you can still take a shower even if the main line gets shut off. Well, a BESS does the exact same thing, just with electricity. It's basically a giant rechargeable battery bank hooked straight into the power grid. It acts as this massive, essential buffer, soaking up all that excess DC electricity during the day when it's abundant, and holding on to it safely until the grid actually needs it.
All right, Section 3, how grid batteries work. Let's look at the physical engineering.
Watch how this whole architecture scales up. It's like a giant puzzle. In step 1, you start with the battery cell. Think of something really similar to the lithium-ion cell inside your laptop. In step 2, engineers group multiple cells together into a module to pump up the capacity. Then, for step 3, you stack a bunch of those modules vertically into this massive server-like structure called a battery rack. And finally, step 4, dozens of these racks are housed inside a specialized climate-controlled shipping container. So when you're driving down the highway and see rows of these white or gray containers out in a field, you're looking at a fully assembled BESS plant.
Now, obviously, these giant containers need some serious management to run safely. Let's decode the alphabet soup of a BESS, starting with the BMS, or Battery Management System. I like to think of the BMS as the strict teacher of the facility. It is watching over thousands of individual cells 24/7. Its one and only job is to monitor the voltage, the current, and the temperature, and it will instantly isolate any single cell to prevent overcharging or overheating. It's the ultimate safety brain.
Then you've got the PCS, the power conversion system. Here's the thing. Batteries can only store DC power, but our homes and factories run on AC, so the PCS acts as this essential translator. It converts all that stored DC power back into AC so it can actually be pushed out to the grid and used. And wrapping up our acronyms, we have the EMS, the Energy Management System. If the BMS is the strict teacher, keeping everyone safe, the EMS is the principal. It's the smart decision maker running the whole show. It pulls in live weather forecasts, grid demand data, and real-time electricity prices to make highly strategic decisions on exactly when to charge the batteries up and when it's most profitable or necessary to discharge that power back to the grid.
Let's walk through this practically. Imagine following a single unit of solar energy on a timeline. At noon, the sun is shining bright, and those solar panels are generating max power. By 1 p.m., we've actually got excess power on the grid, so the EMS tells the BESS, hey, start charging. From 2 to about 6 p.m., all that energy just sits safely in chemical storage as DC power. Finally, at 7 p.m., when the sun is completely gone and you flip on your AC, the PCS kicks into gear, converts that stored energy to AC, and discharges it perfectly to light up your living room.
Now, here is a stat that will absolutely blow your mind. How fast does all of this happen? 20 milliseconds. That's it.
A modern utility-scale BESS can respond to changes in grid demand and inject power faster than a human blink, literally. And that incredible split-second speed is exactly what keeps our entire power grid stable.
Section 4. Chemistry and Grid Safety. Let's peek inside the cells.
When you look at the actual chemistry, there is a very clear winner for grid storage. See, while you might want lightweight NMC chemistry for an electric car so you can drive further, a massive grid project out in an open field prioritizes two things above all else: safety and cost. That is exactly why over 80% of modern grid projects use LFP, lithium iron phosphate chemistry. It's incredibly safe, highly resistant to overheating, and honestly, just much cheaper to produce at scale. But we have to address the elephant in the room: thermal runaway. That fear of one overheating cell causing a massive chain reaction. Well, the industry uses a strategy called defense in depth. It's not just one safety net, it's multiple independent layers. First, you have that constant BMS monitoring we talked about. Then, early gas detection that can spot microscopic off-gassing before a fire even has a chance to start. There's active HVAC cooling, keeping the temps perfect. If an event does somehow occur, clean agent fire suppression systems smother it immediately, because you definitely don't want to use water on electrical fires. And physically, the massive containers themselves are separated by strict distance codes, meaning a failure in one can never jump to the next. And this strategy is working. Thanks to this incredible engineering, the shift to safer LFP chemistry, and these strict safety standards, we've seen a massive 97% drop in BESS fire incident rates since 2018. The tech has matured incredibly fast.
Finally, Section 5, the future of storage. Let's look at the booming horizon.
The future here is just incredibly exciting. We're moving rapidly toward AI-optimized energy management that can predict grid needs with almost perfect accuracy. We're seeing the rise of virtual power plants, where thousands of individual home batteries are networked together to act as one giant coordinated facility. And on the hardware side, next-generation solid-state batteries are promising even higher safety and energy density. Look, if you are exploring career opportunities, this field is practically begging for engineers right now. AI and new battery tech are preparing to transform our power grid more in the next 10 years than it has in the last 100. So what does this all mean for us? Will solid-state batteries or AI ultimately be the key that completes our global transition to 100% clean energy? The pieces are all falling into place, and the grid as we know it will never, ever be the same. Thank you so much for joining me for this explainer. The transition is happening right now, so what part of this massive energy shift are you going to dig into next?